so it's too early to tell. So we still have a lot of material to cover. So there will be, so once again, to remind you, the project is due on Thursday. There will be the last homework assigned tomorrow, okay? And then, you'll have like two weeks to, or the whole week to prepare for the final. Okay, so this is the last topic. We're doing a test of series for convergence. So totally separate from tests for convergence of sequences. So these are for series again. Okay, and but the idea is similar. After all, we're talking about partial sums in order to understand series. This is a direct comparison test, and by comparison, it is a vague word, comparison. So it is the comparison is about inequalities. Okay, so one is larger than the other. Okay, so we already have seen this idea that a larger series that converges, well, causes a smaller one converge too. However, only applicable when the series has both of the series have non-negative terms. Okay, so remember, just to justify that idea is it comes from the monotone sequence theory. Monotone bounded sequence converges, and that's why we have to. That's where the fact that sequence has positive terms. When you build the partial sums, that sequence becomes monotone, increasing sequence. Okay, so we don't have a choice in the matter, but it works out at least under these circumstances when the inequality is clear. We can compare these series very directly. That's the word. The key word is direct. So as an example, you could certainly think of examples of comparison series, meaning just like elsewhere, you are looking. You have a new series. You compare it to an old series that you've seen before, you know its behavior. So whether it is convergent or divergent, that will come, will help you. Okay, so as an example, let's take if 1 over n larger than or equal to, less than or equal to 1 over n minus 1. Okay, so that's the inequality, an obvious inequality, and then in addition that all the terms are positive. So for completeness, to make the theorem applicable, we have to verify all the conditions. That the second condition on the left is just as important as the first one. And then we conclude, since we know that the harmonic series in the middle is convergent, divergent, then the bigger one is divergent too. Okay, so as you can see here, once again, as I started yesterday, I'm replacing the word divergent with equal to infinity. It is only applicable to series with non-negative terms because they have only two possibilities, either convergence or infinity. Okay, so as you can see, that was very quick. Series is known. Harmonic series, then a new series we may have never seen it before, also divergent. Okay, there. On the other hand, I could go with, say, I start with 1 over n squared, which is, 1 over n squared here, and then it is larger than 1 over n squared plus 1. So a similar pair of sequences. One is larger than the other. This time the story is the opposite. This series is 1 over n squared is convergent. Okay, so this time I'm moving from right to left like this, and so then by the theorem, in either case, I'm applying the theorem, the direct comparison test. I conclude that my new series is also, convergent. Okay, well, there. That's pretty much the whole story. The challenge is to you will have one series given to you, and you need to find the other one on your own. Okay, but these examples certainly help, and so I'll continue doing 2 more examples to demonstrate the limitations. The obvious limitations will be of these examples. Of the theorem is what if the inequalities that you found is in the opposite direction. Okay, so for example, if I look at the first example over there and I put it this way, 1 over n plus 1. Okay, so it is a correct inequality. All the terms are positive. Okay, and then I have also my convergence series, the divergence series here. 1 over n divergent, so it's the same. The story is about the same series, 1 over n. It is a familiar series. What can we conclude about the other series? So the series on the right is the harmonic series. It is divergent. Can we say that the other one divergent too? No? Why not? Why not? Well, just when in doubt, look up the theorem. So the theorem contained, theorem is self-contained. So so whatever you're trying to say, you're trying to justify it with the theorem, and the theorem tells you what you can or it tells you what you can justify, and that arrow from right to left is justified for case number 1. So we are trying to proceed from bigger series to a smaller series. However, the bigger series is divergent. So as you can see, it does not fall into in either case 1 or case 2. Okay, so if the bigger series is convergent, then we can say that the smaller one is 2. But if it is divergent, then we cannot say anything. As you can see, the arrow is pointing in the opposite direction. Okay, so the answer is then no conclusion. No conclusion from the theorem. Okay, in a similar fashion, in exactly similar fashion, if I have now bigger series, the smaller series converges 1 over n squared. It is less than or equal to 1 over n squared minus 1. Okay, so as you can see, the inequality is the same as in the beginning in the theorem, but the familiar series that is known to be convergent is this one. Sum 1 over n squared is less than infinity. It is a p-series with n equal to 2, with p is equal to 2. Okay, so we know it is convergent, and then if we try to conclude anything about the other series, even though the comparison is there, convergence is there, but the implication points in the opposite direction. So once again, it does not fit into either case 1 or case 2. So once again, we have the same story, the same answer, no conclusion from the theorem. Otherwise, so you don't know ahead of time which one, whether the theorem will be applicable or not. Okay, so so what do you do? What do you do if I still want to make that conclusion? Say, let's look at the last example. So what to do? We don't have too many choices. And well, once again, the series under investigation is this one. So we don't have too many tools, even though we could try to still apply the integral test. And then you same story, except you are comparing your series not to another series, as in this theorem, but to an improper integral. So instead, well, let's suppose we do want to use the direct comparison test. So direct comparison test, that's what we are talking about. So so how to use the direct comparison test, and the answer is choose another. Well, first of all, the step number one is to guess. First, guess the answer. Well, you might be wrong, but then okay, so there's nothing you can do about that. But the point, if you have the answer, then you can try to justify it. If you don't know what it is, it's so hard to justify it. So it's not computation here, what we're talking about, and that's a separate challenge of this part of calculus, is that there are a lot of computations. You are proving things that you first somehow guess, okay? And you cannot arrive to your conclusion through some sequence of computations or algorithms. So in this particular case, you have to guess what the answer is. Does it converge or diverge? It's actually a yes or no question, and then you try to justify it. Okay. So if you look at it, well, can you guess that series circled, convergent or divergent? Yes. Why do you think it's the case?
Because the limits of the are equal.
Well, the limits are zeros both, and you know that is a necessary but not sufficient condition, as you know. Remember the divergence test. Where's my divergence test? This one. Or test for divergence is you have a convergence of the series only if the sequence itself converges to zero. So the fact that both of these converge to zero is really not enough to say anything, because 1 over n is also limit 0, right? So if you look at the sequence itself, all of these go to 0. All of these go to zero, and so as such, it doesn't really. It is a pass. You get a pass if you go to 0. Then you have a pass, and you are then subject to further investigation. If you don't pass that, then you are divergent. Then there's nothing else to do. So all of these pass this first test, and they all go to 0. So we have to use some other methods to conclude that there is a convergence or divergence. And what is actually true is not only the 1 over n squared plus 1, the circled one goes to 0. It goes to 0 at roughly the same rate as the other one. So it's not really about the inequality. The inequality is in the wrong order. Okay. So but 1 over n squared or 1 over n squared minus 1. The functions are so close to each other, the denominators, that they behave in exactly the same way. So this should remind you of possibly maybe limits. How about horizontal asymptotes? Horizontal asymptotes, when you have two polynomials and there you divide them by each other, say, what if I have n squared divided by n squared minus 1? Okay, so in order to conclude anything about it, you compare the numerator and denominator as polynomials, and both of them have degree 2, and as such they behave similarly. And that negative 1, that's the key. That negative 1 is really not, in long term, is not important. So when n is very large, then the difference between n squared and n squared minus 1 is negligible. Okay, so they both go to infinity or reciprocal to 0 at the same roughly rate. You can also justify that we're referring to, remember what the other way to approach this problem from calculus 1? L'Hopital's rule, right? So you differentiate both of the functions or sequences, and that's how you find the limit. So when you differentiate, negative 1 is gone, and you arrive to 1, and so that's why the limit is 1 of that fraction over here, and that's why you say that those two functions that we are concerned with, these two have the same rate of decrease. And as such, you would guess, but further to investigate, they should behave in the same manner. So this kind of logic, it is still loose, but it helps us to make a correct guess. And so the guess is yes. So the guess is it converges. And then prove it. And that kind of analysis that we just did, we will do shortly. At this point, we don't have that tool yet, and the only tool that is available is, once again, the direct comparison test. So what does it mean? It means that the inequality that here is at the top of my example is wrong. I have to prove convergence using the convergence test, direct comparison test. I want to prove convergence, so my series under investigation should not be a larger one, but a smaller one. So this is where I want to be for my sequence, and the first sequence, AN, should be my sequence that I am investigating. I want to prove that it's convergent, so I have to show that it's smaller than another convergent series. Okay, so that inequality then that is above, we looked at originally, is of no use to us. So we have to look at 1 over n squared minus 1 less than or equal to something. So this is now new inequality that we want to use for the direct comparison test. And so this is where we have to put something here, a convergent series, or sequence rather, series, the series of which converges, we have to put to the right. Okay? So can you think of a sequence to put there? Well, we don't have too many choices right now. The only available pool of convergent series is, in fact, the P series. Where's my P series? Yeah, here it is. The P series right here on the left. So this is the P series. Okay, so it's 1 over n to some power p, and whenever p is larger than 1, we have convergence. Okay, so that's the answer. Really, we don't have too many choices. So I have to put a P series on the right, but I have to have a P larger than 1, that's all. So n to some power, what should that power be? So 1 over n, as it's stated here, is divergent, so it's of no use to us. At the same time, I cannot put 2 there because the inequality would be wrong. So which means that I just have to pick any number for the power. I should pick any number between 1 and 2. Yes, between 1 and 2. Well, maybe not any number, but some appropriate number. We'll pick 1. Number between 1 and 2. How about halfway, 3 halves? Okay, so it's unclear that it would work yet, but if we can demonstrate this inequality to be true, then we will know then what? This is a convergent series, 1 over n 3 halves. Convergent as P series with P equal to 3 halves, okay, and then we show that our series, that the one under investigation, this series, the new series that we brought in, is less than a convergent series, which proves that it will be a convergent series. Okay, so the only thing that remains to be demonstrated is this inequality. Is it true? So show that 1 over n squared minus 1 is less than or equal to 1 over n 3 halves. I picked the simplest number, 3 halves. I certainly could have taken any number smaller than just any small number, 1 unit, 1/10 or 100th above 1, and it will still be okay. But I picked the simplest one. So So to show this inequality, I need to show that the opposite. So I need to show that n squared minus 1 is larger than or equal to n 3/2. Okay, so just look at a few values to confirm that this is the case. So if I start with n equal 1, I have 0. N equal 2, I have 3. N equal 3, I have 8. N equal 4, I have 15. Okay, so the pattern is more or less clear. And now I take the part 3/2 power of n. This will be 0. I'm sorry, this will be 1. So as you can see, the inequality is not true yet. So no. Then I take 2, and then at this point I need a calculator. Okay. Okay, I need to take 2 to the power of 3/2. Where's the... Okay, scientific. Okay, what is your problem? I need scientific. Okay, let's try again. So I want to take 2 to the power of 3/2. Well, I can just take where's my square root? Oh, here it is. Take a square root and then take to the third power. So power... Where's the power? Here, well, let's just take this one. Okay, 2.8. 2.8. So still no. We need... no, it is already okay. Okay, so it is working out. So the inequality is true. And then you just need to sort of extrapolate somehow without computing. I cannot compute infinitely many terms here, so I need to show that at some point once the left-hand side is bigger than the right-hand side, at some point on, that inequality will continue to be true like this, even though I'm not computing any of these values. So you can tell me how this is done. How can I show that this inequality continues on? So once again, let's make sure that we know where we are right now, what we're trying to accomplish here. The problem is almost solved. We've almost demonstrated that our series is convergent, but that inequality in the middle is still under investigation. We have to demonstrate that our series is less than or equal to that new series that we have found. Okay, so I picked the series 1 over n 3/2 for simplicity, and but I need to show that this is true. Okay, so I tried to do it through experimentation, just a few terms in the beginning, and then as you can see, it is even though the n equal 1 doesn't work out, the second one, n equal 2, does work. So this one is okay, and then but I need to have that inequality for every single value of n. How do I do it? Well, the discussion that we just had about right there in the top left is about powers for 1. So at least the way to justify that kind of conclusion informally would be to look at the degrees. At the degrees, if we look at the degree is 2 here and the degree 3/2 there. Okay, so if we look at the degree is what determines the long-term behavior of a function or a sequence. And that is why the high degree will always eventually, that's why it should work out, is because the a function of high degree will always overtake a function of lower degree. And so once again, 2 versus 3/2, we will always overtake it eventually. So the only we could just leave it as this, but so in just to say that degree is degree 2 is higher than degree 3/2. Oops. And but just for completeness sake, and we wanna make a little bit more of that. So how do you justify that degree 2 will eventually overcome degree 3/2 function? So one function. Let's just examine this idea with polynomials. So y degree 2 polynomial will always overtake degree 1 polynomial. So this will work out eventually, but say, so degree 2, degree 1. Degree 2, what kind of polynomial is degree 2? What's degree anyway?
Degree 2 would be a quadratic.
It is quadratic, and the degree 1
Is linear.
it is linear, right? So so that is a comparison that is fairly transparent because, well, we know parabola looks like this, and linear doesn't matter how steep it is, it will be eventually overtaken by the parabola because why? Because the parabola is actually going faster and faster, right? So the steepness, the slope is increasing of the parabola. So following the same logic, which is less visible, but if you take a quadratic, if you take cubic and quadratic, then cubic will be growing faster than the quadratic. And growing faster is the other word for what? No, that's the conclusion. We draw a conclusion from a faster growth, in that even if you're behind, you will overtake it. But it's a different word for the word derivative, or velocity, whatever. So that's really the way to use calculus. Even in this kind of a situation, you can look at the derivatives of the functions involved, and then if one derivative is larger than the other, well, eventually it's like two runners. If one of the runners is faster than the other, it will eventually be ahead. That's the thing about so when you have degree 2, degree 3/2. It will be overtaken by this thing. And once again, how do you find that out? You either actually compute the derivative of those two functions, ignore the fact that these are n's, they are integers. You can think of them as just like a function of x that has been sampled. So for example, if I have n squared plus 1, I could look at x squared, n squared minus 1, x squared minus 1 is sampled. It looks like this, right? And then you just sample it, and that creates a sequence like this. It doesn't matter. So if you have two sequences, if they're given by explicit formulas, so you can just as well compare those formulas rather than just literally the series. So then, as you can see, one is degree 3/2, the other degree 2. How do you know one is larger than the other? You differentiate. So if my f of x is here, it is the function is x squared minus 1. Its derivative is 2x. In the meantime, here the function is x 3/2. The derivative is 3/2 x 1/2. Okay, so we already see the difference between the two functions. But if not enough, and that sometimes happens, if you want to really take it all that point all the way through, and what derivative does, then you take the second derivative, right? So take the second derivative, and this will be 2, and here it will be what is it? 3/4 x negative 1/2. Okay, so. And then the same story. To overtake your opponents, you don't have to have initially velocity higher than his, which is ideal in the simplest situation. But what if your acceleration is higher than his? it means that eventually your velocity will become higher than his, which means that eventually your your position will be ahead of that person. So that's what derivative does to it. And that's how inequalities can be demonstrated when you have some complicated functions involved, because you differentiate things, typically become simpler, and before you know it, you have a comparison which is quite explicit. The second derivative, look at it, a number versus a function that is actually has a horizontal asymptote equal to 0. So, well, like this on the right. On the right, it is the second is 3/2. So the second derivative is higher, which means that the first derivative will be high eventually, which means that the original functions will have that inequalities between them for large enough values of n. And that is sufficient. That's the thing about convergence of sequences as well as convergence of series, is that the eventual behavior of the function, that what matters. It doesn't matter how you start. You can have a wild behavior early on like this, but then if you converge, you converge eventually. Okay, so and that's the thing about derivatives. Yeah, the key word is eventual. Okay, so that is a little bit complex, seemingly a small part of the proof, which is just to justify the application of the direct comparison test. We had to prove that inequality, and that involves some extra work. A little bit cumbersome, if you ask me, and the way to get around this. The advantage is that the test is direct, but sometimes you have to go into computations like that in order to justify it. So there's a better way, which takes care of derivative immediately rather than after the fact, and that is that analysis that we started with, and that is looking at the derivatives. Looking at the limits to begin with. So those two sequences that we look at should indeed be compared as such, as just is their long-term behavior similar? That's roughly the question we want to answer, rather than similar versus kind of a dominated. One dominates the other. So that's the direct comparison test, is about domination of one over the other. So it works out fine. Sometimes it does not, and then it turns out that it's better to really concentrate on the find a similar sequence rather than a sequence that is bigger or smaller than your sequence. So in other words, that inequality here is justified. Not the inequality, but rather the why the series converges is justified by this. Well, let me just rewrite what we already have seen here. So we have an is equal to 1 over n squared, 1 over n squared. Bn is equal to 1 over n squared minus 1. Okay, so we ignore the inequalities between them, but rather consider instead the fraction an over bn. Okay, so 1 over n squared over 1 over n squared minus 1. Okay, and we bring in stuff from calculus 1. So this one simplifies significantly. It is in fact n squared minus 1 over n squared, and we just evaluate this limit. So to compare long-term behavior of two functions or two sequences is done. Explain what is the meaning of long-term behavior of two functions, similar or not. It means that the ratio, the limit of their ratio is a number. As one of the possible outcomes, we have two sequences, we form a fraction from them, we take the limit of the outcome and look at what that number is. And if that number is, if it is a number to begin with, then it tells us something about it tells us that they're similar. So in this particular case, what is the limit of this as n goes to infinity? N squared minus 1 over n squared.
Is it 1?
It is. So how did you do it? How did you do it?
I just compared if you plug
Yeah.
in certain numbers and over each one, it's just going to equal 1 pretty much.
Plug in numbers?
Yeah, like in my head, I just put like, no matter what numbers you put in there, they're both going to be the same one on top and the bottom.
Yeah, so -1 makes a negligible difference when n is large. And we're talking about the limit after all, as n goes to infinity. So it means that n is, we can think of it as a very, very large, which means that, pick n is equal to 1 million. Okay, then you can see that number already will be very, very close to 1. Another way, when you face something more complex than that, you can do L'Hopital's rule, which means literally I would just differentiate. L'Hopital's rule, I will just differentiate, so I'll have 2n divided by 2n, and that gives me 1. Another way is to related way is to simply look at the powers. When you have polynomials or anything, power functions of any kind, then looking at the powers is also sufficient. So these have the same power and 2, and that's why the limit will be a number. We don't really care about whether it is what that number is, as long as it's a number, okay, and not equal to 0. Then we are fine. That will tell us that these two series are similar. And to make sure that this, to illustrate, make a stronger point here, how about I pick 1n cubed and bn is equal to, how about 3 over n cubed plus n? Okay, so slightly make things more complicated. The first series, once again, is familiar. It is a p-series, so it's convergent. How do we evaluate the comparison? How do I compare these two sequences? As far as their series are concerned, I form an fraction. I have 1 over n cubed divided by 3 over n cubed plus n. I take 3 out. I have n cubed plus n over n cubed. And once again, at this point, the methods from the calculus apply. It's pretty much up to you to choose the right one. And in this particular case, but the conclusion is the limit is, what's the limit? So once again, L'Hopital's rule, powers, anything really. Yeah, the limit is 3. That's right. So, as you can see, the conclusion, however, we draw is exactly the same. So in either case, the conclusion is AN and BN are similar. We are still to explain what similar means, but that's going to happen in a minute. Similar meaning that either both of them converge or both of them diverge. That's really a similar behavior, and that's the only thing that we care about, even though we would not be speaking anything about the actual values of those series, sums of the series, if they, in case of convergence. So let me state the theorem. It's called the limit comparison test. So no inequalities this way. So direct comparison was about comparison through inequality or inequalities, and that's why it was called this way. And here we are comparing two sequences through the limit of their fraction, of their ratio rather. Okay. So we have two inequalities. Once again, we require them to be non-negative. Denominator also has to be positive, not equal to 0. Okay, and then we form the limit. Suppose L equal to the limit of AN over BN is a number or infinity. Once again, this sequence is a positive, has non-negative terms, which means that it has only two possible outcomes. It's either, Now it has three possible outcomes because it doesn't have to be monotone. It can have the third outcome, and that is simply limit doesn't exist. So we assume that the limit is in fact does exist either as a number or as infinity, which means that it is once again informative. Then we have three cases. Number one is L is positive, a number positive. So if I put an equality there, it is a number. And then what happens is once again we have those conclusions about the convergence of the two sequences. And but this time let me just put we'll be deriving the behavior AN from BN or vice versa. So BN is convergent, okay, implies that AN is also convergent. Okay, so remember that similar behavior of the two sequences guaranteed when the limit is a number larger than 0. Okay, certainly you can imagine that if L is equal to 0, then that's not similarity. If I take the limit of, say, n over n squared, this one goes to 0. So one sequence is 1 over n and the other 1 over n squared, and they do not have a similar behavior. In fact, one kind of dominates the other. The denominator here dominates the numerator, and so these two functions are different in any way. So then the second case is L is equal to 0. In that case, like I said, if you look at our ratio over here, then Bn is the denominator and the limit is 0, which means that Bn dominates An. Okay, if it dominates, it means that the convergence is also assured. It is the same thing as you can see. And the third possibility is L infinite, which is, now this one is exact opposite because this time the An over Bn goes to infinity, which means that the numerator dominates, which means that Bn is infinite, then so is An. Okay. So these are the two extreme cases. I'd say they're dissimilar. So either one or the other dominates, and this means similar. I don't think there is a special term for it, but it does. You may have seen the notation. For dissimilar, you might remember this notation. Say in case 2, Bn. Have you seen this notation? Right. So that's another word, notation for this kind of informal term. One dominates the other. What does it mean? It means that their ratio, the limit of the ratio, is equal to is going to infinity. Is going to 0. An is on top, so Bn dominates An, and that's how you write it. Or vice versa is for the case 3. For case 1, I'm not sure. I think sometimes that this is what you see like this notation. So the quantities of which one is larger, and when they add infinity, they behave similarly in the sense of their ratio. Then that's kind of a notation sometimes is being used. It is somewhere. Okay, and here this one is the opposite. So Bn is dominated by An. So that's notation. More or less common, even though it varies from discipline to discipline. Yeah, I think that's more or less like this. Okay, and then our life is easier, and even the example that we just considered, and spent considerable time working out that inequality, it is easy now. N squared minus 1 and 3 halves, rather than we dealing with the inequality and the testing and the differentiation, it's all hidden inside of the limit. So whichever way you choose to evaluate the limit, it is okay. So an is equal to once again, what is it? 1 over n squared minus 1. Yeah. Yeah. Actually, the point is you don't need n3 halves. You don't need n3 halves. You have a better way to compare the better series to compare it to, because the better one is bn is equal to 1 over n squared, and this one is already familiar, but I already carried out that example right here. 1 over n squared minus 1, they are comparable, or similar, and so at the infinity they behave similarly because the limit is equal to 1, so it falls under under case 1. So this is case 1. So either both of them converge or both of them diverge. That is a little bit this what I have here is, in fact, it contains two statements simultaneously. It doesn't matter which one is at the numerator and which is the denominator. The result is pretty much the same. If the number is positive, you flip the whole thing upside down. What happens to the limit? You flip the limit too. And you can, because it's not 0, right? So it's the same story. Let me maybe elaborate here. So case 1, L greater than 0. What is greater than 0? So the limit L is equal to limit an over bn, and it is greater than 0. Okay. So it's the same as to say that 1 over L is the limit of bn over an, n goes to infinity. In either case, you have a positive number and positive number, but the conclusion that you draw is different. So if I would write here this way, so when L is positive, either both converge or both diverge. Okay, so that's truly the similarity. So they behave similarly, and therefore at infinity, and therefore the series that they produce also behave similarly in that sense. So even though the actual values of the sum might be different, but they simultaneously is the differences between infinity or not infinity, and they make that choice simultaneously. Okay. All right, so I guess I'll stop here. We'll do another example next time.